Hi everyone. In this video, we will cover the learning algorithm for a simple, fully connected neural network. The purpose of this neural network will be to solve a simple binary classification problem. Now, this video is meant to be a complement to another video that I put out where I implemented this exact same example into Python code. Here, though, I will be strictly covering the mathematics behind the learning procedure for this neural network. First, I will go over the architecture for this neural network and then summarize the different model parameters that we will need to learn in order to have a functioning neural network. Next, I will go through all the details step by step for how this learning procedure will actually function. So let's jump into the presentation. So this is the architecture of the neural network that we will be implementing in this video. We'll see right away that it consists of three different layers. We have an input layer that has 3 different neurons in it. We have a hidden layer with 5 different neurons, and then an output layer with a single neuron. Now we should emphasize that with the input layer, we have neurons here that simply represent the input raw data to the network. We don't actually compute anything within these neurons that are labeled X1, X2, and X3. The hidden layer consists of 5 different neurons, and all of them have the sigmoid activation function. And then we have also a sigmoid activation function for the neuron in our output layer. This is a fully connected neural network, and the general flow of data through the network goes from the left-hand side to the right-hand side. Now, if we move this over to the side, we can focus in on what's actually going on in the neurons within our hidden and output layer. So we have a series of inputs to this neuron, and that's labeled here as X1, X2, and X3. And within the neuron itself, we have a 2-step calculation taking place. The first step is to compute this value called Z. And Z is simply a linear combination of our inputs, and our inputs here are represented by this vector X. X just is a vector that has the elements X1, X2, and X3. And we compute the dot product of this vector with a corresponding weights vector, W. And this vector has elements that represent the weights on each of the inputs corresponding to X1, X2, and X3. So the weights simply control the relative strength of the signals coming in via the inputs. Now added to this is a bias term for the neuron, and that's just represented by this B term. So we have this calculation, this is the first step, and then we pass Z through this function called F. And F is called an activation function. The purpose of F is to introduce nonlinearities into the model. So this is a very important step. This is what enables neural networks to learn highly complex nonlinear relationships in the data. So that's a very important step, and we call the output of this as Y. And so Y is what's passed out to other neurons in a subsequent layer of the network or as a final output. Now, if we want to be a little bit more rigorous in terms of the calculations that are going on within the network, we can look at this equation. This is just the definition of Z, again, with what we saw above already. But here I've added in superscripts. In this case, the superscript is I, and that just represents the layer that we are currently in. So I can range from 0, which is the input layer, to 1, which represents the hidden layer, and then 2, which represents the output layer. And J iterates over the neuron, the specific neuron in layer I. So in the case of the hidden layer, j will iterate from 0 to 4 because there are a total of 5 neurons. And for our output layer, j is just 0 because we only have a single neuron in this layer. And we pass this z value through the activation function to get a corresponding y value. So at the bottom, we just have a little bit more mathematically rigorous representation of what I showed previously in the figure above. So let's look at our hidden layer and our output layer a little bit more closely. So we'll start with the hidden layer, and can we encapsulate in some way all the parameters that we're going to need to learn for this layer? So if we combine all the weights and biases together for all 5 neurons, we're going to get these structures. So first we have the weights, and this is just the weights for all the incoming connections for this layer. We can represent this as a column vector, where each element in this vector is itself a vector, or we can expand out each of these elements such that we get a matrix, a 5 by 3 matrix, where every row is the weight for all the inputs corresponding to the specific neuron in the hidden layer. So this is just how this is being structured. And then at the same time, we have a column vector for all the biases that correspond to the 5 different neurons in our hidden layer. Now, in a similar way, we can also look at our output layer. And here, these are the sort of structures that we get. So our weights matrix here is in fact just a row vector. And this just has elements for each of the incoming inputs that we are receiving in this layer from the hidden layer. And we also have a single bias term that we have for the single neuron. So these are the structures that we need to pay attention to for the output layer. So these are the parameters that we're going to need to learn. We have this matrix, this weights matrix, and this bias vector for the hidden layer. And then we have corresponding structures for the output layer. So we need to learn how to properly set these parameters. And so we're confronted with a problem: how exactly are we going to do this? Well, the approach that we're going to use is called gradient descent. In general, the approach involves computing the derivatives of some kind of loss function. So we have to define that. And what we want to do is we want to minimize the loss in terms of the parameters that we need to learn. So just to illustrate that in a more simple way, we can look at the figure on the left, and this just shows a simple surface plot, and the surface plot is done in terms of 2 different model parameters. Here we see it as W0 and W1. The loss itself is represented as this surface in this parameter space. The idea here is that we want to be able to figure out how these model parameters should be set such that we arrive at the lowest possible value for our loss. So that should make sense. And the way that we approach this is with this update rule. So the update rule simply involves computing the derivatives of our loss with respect to our model parameters. So here we have 2, right? We have the loss function is represented by this L, and we compute its derivative with respect to W0 and then W1. We multiply it by a parameter called alpha, and alpha is what's called a learning rate. This is typically a small value that can be something between, say, 0.1 or 0.01, for example. And this is just meant to ensure that our update steps are small. The reason for this is because we don't want to have very large update steps, because this might mean that our model never actually converges on a local minimum. Instead, it can just oscillate around that minimum if these steps are too big. And so we just update our values according to the product of the learning rate and then these derivatives. And in this fashion, after a sequence of iterations, we can actually approach a minimum in our loss. So that's the whole general idea of our learning procedure. Now, before we actually step into that, we have another problem, which is how do we actually initialize all these things? Now, the naive approach would be just to set all the weights and biases to 0. However, if we look closely at the equations that I showed in the previous slides, we'll actually see that if we do that, all the neurons in a particular layer will yield the same values. And this creates a problem because it means that the individual neurons in a layer cannot construct distinct features for the data we're looking at. In effect, what happens is that all the neurons in a given layer function as one single neuron. And this really defeats the purpose. It defeats the strength of a neural network, which is this capacity to learn complex features and these interesting relationships in the data to solve very difficult problems. So we need to be able to make sure that these neurons have the capacity to do this. So we need to be able to break this symmetry. So that's the first issue. The second issue is that these values for the weights and biases cannot be too big. And the reason is because many of the activation functions that we have, such as the sigmoid activation function, which is what we'll be using in this example, or the hyperbolic tan, are asymptotic, which means that for very large values, the functions actually plateau out. And that in turn leads to very small gradients. And so what we can encounter is this problem called the vanishing gradients problem. Basically means that our model learns very, very slowly, if at all. So this can really affect performance. And so we want to ensure that we avoid this. And the way that we actually get around these two problems is just by simply initializing our model parameters to be small random values. And that's a pretty good approach for accomplishing this task and for setting up our initial state of the model. So at a very high level, this is going to be our learning procedure. We are going to iterate over a certain number of epochs. And an epoch is just an exposure of the model to our entire training set. So we're just going to pass through all our training data through the model and update the weights according to gradient descent. And normally with a neural network, we do this many times over. Now for each epoch, we can actually update the weights more than one time. And the way that we do that is by setting this batch value. So we can partition up our training set into a number of batches and then update our weights after only that batch has passed through. So as we iterate through these two loops, what we are computing is first what's called a forward pass, and that's just simply working through the neural network from the input layer to the output layer and recording all the activations that we have along the way. Next, we do a backward pass, and the backward pass passes in the opposite direction. It goes from the output layer to the input layer, and the goal here is to compute the derivatives that we need in order to do gradient descent. So that's the objective we have here. And then finally, once we have that in place, we can actually update the model weights. So that at a very high level is our learning procedure. Now let's look at these steps in a little bit more detail. We have our forward pass, and here I've just illustrated again for our example what we are exactly doing. So we go from the input layer again to the output layer, and our approach is this three-step process. So we start with the input layer, I equals 0. We clamp our input features to this layer. 2, we now are at the hidden layer, I equals 1, and we compute the activations we get. So that is going to be y1, and y1 is simply the output of our activation function. F, the input to F is z1, and z1 is computed with this linear expression here. Next, we go to the output layer, I equals 2, and here we actually compute the prediction of our model, ypred, and ypred is just equal to y2. y2 is equal to the output of our activation function in this layer, which has as an input this value for z. Now, I should emphasize here that all the superscripts are the I values that I have mentioned. These are not exponents, they are superscripts that illustrate the layers that we're talking about. So that's all that we have for the forward pass, and it's actually a pretty straightforward calculation that we need to do. Now let's look at the backward pass. So as already mentioned, we're going from the output layer to the input layer. Now, some things to mention before we dive into the details. The first is, because we are dealing with a binary classification problem here, we are going to use the cross-entropy loss, and that is defined here in this equation. It is a function of the true labels and the predicted values that are coming out of the network, and it's just this logarithmic function. We're going to need to get out of this backward pass these following derivatives. So these are the derivatives of the loss with respect to our two weights matrices, so this is W1 and W2, as well as the derivative of the loss with respect to our biases. So this is B1 and then with respect to B2. So this is what we need to do. And the question that comes to mind right away is, how exactly are we going to do this? Our loss itself is not written in terms of W1, W2, or B1 or B2. So we need to be able to figure out a way to compute these derivatives. And the way we're going to do it is by making use of backpropagation. Now, before we work through an example of backpropagation for this case, let's note the following equations. So the first is the derivative of our loss with respect to our predicted values is of this form. You can work that out yourself if you're interested. Our activation function, as mentioned, is going to be the sigmoid activation function, so it has this mathematical form. And the derivative of this activation function with respect to z is equal to y times 1 minus y. So it just has this form. And finally, it's also key to keep in mind the definition of z. This is going to be very important when we are working through our backpropagation. So I'm going to mention this definition a few times. Okay, so let's start at our output layer, I equals 2. We can start by computing the derivative of our loss with respect to z2. And the way we do that is by making use of the chain rule of calculus. So we can expand out this derivative to be a product of two other derivatives. The first being that of the loss with respect to our predicted values, and the second being of our activation function with respect to z2. Now you might notice some notation here. The second derivative is written in terms of a full derivative, and that's just because our activation function is only a function of a single value, whereas the other derivatives, our loss, is a function of two parameters, and so I've written this as a partial derivative. As well, the product symbol here, the dot with the circle, is just meant to represent element-wise multiplication. So just understand that that's what this equation is representing. So we have this expression for this derivative, and now we can compute the derivative of the loss with respect to the weights for the output layer. And again, the way we do this is with the chain rule. So we expand this out as being the derivative of the loss with respect to z2 times the derivative of z2 with respect to w2. This multiplication symbol here, the times symbol, is meant to represent matrix multiplication. So just keep that in mind. Now we can use the definition of z to simplify the second derivative. And if we actually work that out, we see that this is just equal to the activations coming out of the hidden layer, y1. More specifically, if we enter this into our equation, we see that we have to multiply by the transpose of this activation vector. So this is the expression now that we can use for the derivative of the loss with respect to W2. And also notice here that this should be with respect to Z2. I missed putting the 2 here as a superscript. Now we can also follow the similar approach to work out the derivative of the loss with respect to the bias in our output layer. And so we can then expand that out as being the derivative of the loss with respect to Z2 times the derivative of Z2 with respect to B2. Again, if we look at the derivative of Z2, we can see that the second derivative is actually just represented by an identity vector. And so when we look at this, we actually see that the derivative we need here for our biases is just the sum of our derivative of the loss over Z2 we're summing this all over n, and n is just the number of samples that we have in our current batch. So these are the derivatives that we need for our output layer. Now let's take a further step back and look at our hidden layer, so I equals 1. We need to be able to connect what we have already for our output layer to our hidden layer. So let's look at that first. The way that we're going to do that is by computing the derivative of the loss with respect to the activations coming out of the hidden layer, y1. We again use the chain rule. We get these two terms. We have the derivative of the loss with respect to z2 times the derivative of z2 over y1. And if we look at the second derivative, we actually see that if we look at the definition for Z2, this derivative actually works out to be W2, the matrix of weights for the output layer. So we can rearrange this equation to be simply equal to the weights for our output layer, the transpose of these weights, multiplied by the loss, the derivative of the loss with respect to Z2. So this is going to be our bridge. We can now look at the derivative of the loss with respect to Z1 for a hidden layer. And this then just works out to be the derivative of the loss with respect to Y1 multiplied by the derivative of Y1 over Z1. And so again, this operation here is element-wise multiplication. And so we can use the derivative we have above to fill this in. We then are able to compute the derivative of the loss with respect to W1, again by using the chain rule. We can then get the derivative of the loss with respect to Z1 times the derivative of Z1 with respect to W1. The second derivative, if we look at the definition of Z, just works out to be the vector of inputs coming into the network via the input layer. So we can just simplify this derivative calculation just as being this form. And like before, we can compute the derivative of the loss with respect to the biases in the hidden layer by using the chain rule. If we look at the definition of Z again, we see that we end up for our second derivative here. Well, this is just the identity vector. And so in essence, the derivative of the loss with respect to the biases in the hidden layer is just equal to the sum of the derivatives of the loss with respect to Z1 summed over all the samples in our batch. So these are the derivatives we need for our hidden layer. So with that in place, we can now update our model parameters. We do that in this fashion. So here I've just written it out for all the different weights and biases that we have. You can see here that we have on the right-hand side the derivatives that we just worked out, and we multiply these by 1 over n. Again, n is just the number of samples in our batch. So in essence, we update our weights and our biases by the average of the computed derivatives over the data that we have in the current batch. So just keep that in mind. That's how it works. And of course, we also multiply in our learning rate, alpha, and that again is just meant to ensure that we are not taking step sizes that are too big. So this concludes the video. If you're interested to see how this algorithm can actually be applied in code to build a working neural network, please check out my other video on this topic. I hope you enjoyed this video and learned something from it. If you did, please like, share, and subscribe to the channel. Your support is greatly appreciated. Have a great day and see you in the next video.